Okay, this video should be pretty short and is going to be dedicated specifically to defining rotational kinetic energy. So basically we're going to derive a new formula for kinetic energy as it relates to rotating objects. Now you all know what rotational kinetic energy is from last year. That is, we know that K rotational is equal to 1/2 I omega squared. But now we're going to set it up and see exactly where it comes from, because remember that everything that we do in physics basically comes from fundamentals, those initial observations that we've made since the beginning of the year. We're talking about motion and forces and masses, just these really simple observations, and everything else we do is built up from that. Okay, so what we have here is a rotating disk, and when we look at that disk, it's going to be comprised of an infinite number of small pieces. So basically, if we just take a look at a little chunk here, and then another little chunk that's out here towards the edge, each one of these chunks has a kinetic energy. Now, the kinetic energy of each chunk is based on really just how fast each chunk is moving. So if we look at just one chunk, then what we have is the kinetic energy for that chunk is equal to 1/2 mv squared. So no surprises yet. All right, now we're just going to say that it's a little chunk, and if we want to know what the velocity of that little chunk is, because remember we're looking at rotation, this is going to be particles. We're going to say that they're rotating in that direction, so everything is a positive quantity. So the speed of the particle, in order to determine that, we have to use our bridge equations. And you should recall from last year for the bridge equations that v is equal to omega r. So this is the tangential speed of the particle for the radius at which it's located. So it's the speed of the particle for the radius at which it's located from the axis of rotation. And omega, of course, is the angular velocity of the rotating object. So all I have to do is solve this for v squared, or just substitute omega r in for v. And when I do, we get k is equal to 1/2 m times, now v squared is equal to omega squared r squared. So we get 1/2 m omega squared r squared. All right, so now that's going to be the kinetic energy for the individual chunk. The problem that we have compared to other scenarios that we've looked at when it comes to kinetic energy is that these particles are located at different radii. We know that they all have the same angular velocity. They all complete the circle in the same amount of time, but the part that's closest to the axis of rotation has a smaller circle to go through. That circumference is going to be smaller, and so its tangential speed is going to be smaller, and the one that's further away is going to be larger. So we're just going to put in some arrows here. So this is going to be for the inner chunk, and that's going to be for the outer chunk. So we could say that this is R1 and this one is R2. Remember that capital R we would use to designate constant size, or the radius of this rotating disk. Okay, so if I want the total kinetic energy, then it's just going to be the kinetic energy of particle 1 plus the kinetic energy of particle 2 plus for all the particles. The problem is we've just got so many particles here that it's not exactly practical to do that. We're going to learn how to do that, but instead we're just going to rewrite this equation here just a little bit, and we're going to say that K rotational is equal to the sum of the individual masses times the individual radii squared times omega squared. So by chunking this out, I put the parenthesis around this MIRI squared. This is a special term, and that is basically how we define the moment of inertia. In the moment of inertia, we use the capital letter I. So I is defined by the sum of MIRI squared. We're going to do a whole video on how to utilize this definition for practical purposes. But basically, all the moment of inertia is the rotational equivalent of mass. Okay? Now, each one of these chunks are the same size, but in order to rotate this little chunk in the circle, it requires far less torque to make that rotate. And this one that's further away from the axis of rotation, it's going to require far more torque to rotate. Or you might think of it as force. Remember that torque is just rotational force. So if we look at this from an energy perspective, we would have to say that the energy of this particle that's closest to the middle, the kinetic energy, is going to be less. Therefore, the one that's further away requires more work in order to give it the appropriate kinetic energy to complete a bigger circle in the same amount of time. Now, you can understand what the moment of inertia is, practically speaking, if you just go to your closet and you grab a broom. And if you stick your hand very close to the head of the broom and try to just, twist it a little bit, you're going to see that it's very easy to twist the broom. Kind of shake it so that it sweeps up and down, just twisting your wrist. But if you hold the broom out towards the end of the handle and try to rotate that broom so that it's sweeping in a vertical direction, like you're trying to sweep the wall, for example, and if you hold it all the way out there towards the very end, you're going to find that it's considerably more difficult to make it move. But here's the thing, the broom didn't change mass. So at the end of the day, when it comes to rotating, the inertia of rotating, it has to do with more than just the mass of the object. And that's what the moment of inertia does for us. It just gives us the equivalent of mass for rotation. So ultimately, what we get then is that K rotational is just equal to 1/2 I omega squared. Okay, so let's take a look now at an example. And what we have here are two spheres. We're going to consider them to be point particles. They're separated by this distance r from center of mass to center of mass. The small one has a mass of m, and the large one has a mass of 2m. Our axis of rotation is going to be right here. So this is an example for calculating the moment of inertia for discrete particles. Okay, so when it comes to moment of inertia, one of the properties we have, and that basically comes from how we defined rotational kinetic energy, that's going to be that the moment of inertia, or I total, for a system of particles, this is a two-particle system, it's just going to be the moment of inertia for particle 1 plus the moment of inertia for particle 2. Now, from there, we know by definition, I for an individual particle is equal to mr squared. So in our specific example, I1, we'll just go from left to right. I1 is going to be equal to mr squared. I'll do it like this: m1 r1 squared plus m2 r2 squared. Now m1 is just equal to the mass m, and r1 is equal to 1/2 r. So r1 is 1/2 r, capital R, not little r, because this is a constant of the problem. It's no longer a variable. And we square that quantity. And then we have 2m times, once again, it's 1/2 r quantity squared. So this is equal to 1/4 mr squared plus, now this is 1/4 r squared times 2, so that's going to become 2/4 mr squared. And so now we just add it up and we get I total for this simple system is going to be 1/4 plus 2/4, or 3/4 mr squared. So that's it. That's how you find the moment of inertia for point particles. In a future video, we're going to look at how we find the moment of inertia for objects which are extended bodies, because they have a continuous mass distribution. And when you have a continuous mass distribution, like a long thin rod, a disc, or a sphere, it's no longer possible to do the direct approach of using the definition of I equals mr squared.